Okay, continuing with 4.2. So from the previous examples that we did, if you didn't notice, a reflection is a rigid motion. So reflections are rigid motions. And again, what that means is regardless of whatever you're reflecting, could be a triangle, it could be a quadrilateral, a segment, whatever. And regardless of what your line of reflection is, the image would be congruent to the pre-image. That's what a rigid motion is. And then kind of like with translation, you could have multiple reflections or even a translation followed by a reflection or a reflection followed by a translation. And that's a composition of reflections. But if you specifically have a translation followed by a reflection, that's more commonly known as a glide reflection. The glide is a translation, and then the reflection is obviously the reflection. So here's what I have. I have triangle JKL. I already graphed that. And then I want to graph the image, and I specifically want to use the correct notation after the glide reflection. So first, I'm going to translate this triangle JKL using this ordered pair notation, x minus 6 and then y minus 1. So that means take 6 away from each x coordinate and 1 away from each y coordinate. So the coordinates of j prime, 3 minus 6 is negative 3. I'm going to write it out here. So this is after the translation or the glide. So j prime, that's the correct notation. 3 minus 6 is negative 3. 1 minus 1 is 0. And then before I graph that, I'm going to find the coordinates of j prime, k prime, and l prime, and then graph it. So k 4, 2. 4 minus 6 is negative 2. 2 minus 1 is 1. And then l prime, 1 minus 6 is negative 5. And then 3 minus 1 is 2. So then I can graph each of those points. So j prime, I'm actually going to use a different color so you can see it a little bit better. So here's j prime, k prime, negative 2, 1. And then l prime, negative 5, 2. And if you recall from 4.1, a translation is a rigid motion. So what should happen here is j prime, k prime, l prime, that triangle should be congruent to jkl. Okay. This is the image, this is the pre-image. But now here's what we want to do. We want to reflect this image, not the pre-image. So it's a translation first. This is a translated figure, now followed by the reflection. So this is what we're going to reflect, not this, even though you should be able to reflect that. So in order to reflect, we need to figure out where the line of reflection is first. X is equal to 1. There's 1 on the x-axis, and then it's a vertical line. So this right here is my line of reflection. And then, so after the reflection, we're actually finding j double prime because there's 2 transformations here, k double prime, and then l double prime. That's the correct notation. If I had, say, 3 transformations, then I would be using triple prime, j triple prime, k triple prime, l triple prime. But to figure out the coordinates of j double prime, here's the line of reflection. Again, it's a vertical line. J is 4 units away from the line of reflection on the left, so go 4 units to the right to figure out the coordinates of j double prime. So j double prime would have the coordinates 5, 0. K double prime, after I label j double prime, is 3 spaces away to the left of the line of reflection. So I go 3 spaces to the right. This would be k double prime. And then lastly, excuse me, l double prime. L is 1, 2, 3, 4, 5, 6 spaces away to the left of the line of reflection. So those 6 spaces to the right. 1, 2, 3. Right here. That's L double prime. And I didn't write the coordinates of k double prime, which would be 4, 1. And L double prime, 7, 2. All right, and then the last term from 4.2 is line symmetry. So a figure has line symmetry if it can be mapped onto itself by some sort of line of reflection. So let me give you an example. If I had a square, that square, where all the sides are congruent, all the angles are right angles, has line symmetry. There's not actually just one line of symmetry for this square. Okay. I have one line of symmetry that would go horizontally right through the middle because this bottom part is a reflection of this top part. I also have a line of symmetry that's vertical through the middle. And since it's a square, it would actually also have two other lines of symmetry, kind of like y is equal to x and then y equals negative x if the center were 0, 0. But those would be all the lines of symmetry for this square. And as you can probably guess, other figures have lines of symmetry as well. Like a circle would have an infinite number of lines of symmetry going through the center. Could be horizontal, could be vertical, could be at any angle. Not for a square though, just at 45-degree angles. Certain letters of the alphabet have line symmetry. It depends on how you write them as well. Like a capital B, depending on how you write it, could have line symmetry. A line of symmetry could go horizontally through the middle. If you write it like this, which some people do, then it actually would not have line symmetry. If this top part of the B is smaller than the bottom part of the B. And A, capital A, would have line symmetry. The line of symmetry would be vertical through the center, and so on. So certain letters, certain polygons, certain figures have line symmetry, but not everything has line symmetry. Okay. For example, if I wrote the letter, let me think about what would not have line symmetry. Like this capital B, for example, lowercase a would not have line symmetry, and so on. There's certain letters that actually would not have line symmetry.